But as I say, I'm Robert Anderson, Technologies Material for HPMN Code. What I'm going to do this afternoon is provide you with some background information to the way in which we generate these data, and then hand you over to my colleague Paul Roberts, who will talk about the software and the way we put it in. The program for this afternoon is, as I show on the screen here, it is producing good materials data, which is the subsections which I will talk about, and then Paul will take over and talk about Materials Manager and show you the various details of that. How do we produce good materials data? Yep, that's a good question. In doing CAE analysis, we have the three input boxes of loads, geometry, and materials. And I'm afraid that materials very often gets left to be the afterthought. And this is not actually a good idea, because the parameters you feed in can have just as much effect as the loads and the geometry. So, I know it's an obvious thing, but what is the basic material? We need to take that into account. It will be an alloy, of course, because we're talking metals in this. We look therefore at the composition of that. We then look at the manufacturing process, and by manufacturing I mean literally any treatment prior to use, whether it's cast or forged or formed or rolled, whether it is then treated in any subsequent way. The result of that is a change in the microstructure, and that microstructure, of course, is what drives the fatigue process in that particular material, in that particular application. Part of the influence, of course, is the cleanliness. So if it's a good clean alloy with no crud and mess in it, then we're in with a good chance of having a very good fatigue response. And finally, the one that always catches one out is the surface treatment or finish. That has a very big effect, and the stronger the material, the bigger the effect is. So your conclusion, of course, is, in other words, to generate the best possible parameters for optimal design, the test coupon should be extracted from suitable reasons in the actual component. Great idea. You've got to design a prototype, so there probably isn't a component existing. However, here is an example of a component which I've marked up using actually cylindrical specimens, but they could equally well be little flat ones. I've marked up potential locations, seeing how one might approach this. And as implied by the way I just said that, you probably haven't got something from which you can make it. So you need to take the next best possible approach, which is to try and get the material you selected for your task into exactly the same condition as that that's going to be used. You will then make specimens of it, and I've throw up some pictures of some typical cylindrical fatigue specimens as we use. These are threaded end ones, and the M and the number give you the thread size in metric units. You can see we range from M6, which are really quite small, up to M18. The drive really is to get as large a volume of material from your chosen material to test. It gives you a better idea of how it's going to behave. But obviously, if the stuff is 3 millimeters thick in the walls, you're not going to be able to do that. I have a similar set of pictures which apply to producing flat specimens from that. I talked on the previous slide, or a couple of slides back, about the finish of the specimens. If you're generating a good baseline data curve, you will do it with polished gauge length. And by that I mean one in which all the machining marks have been removed. That doesn't necessarily mean a mirror polish, but all the machining marks have been removed by using fine emery cloth on a machine specially designed to do this, which takes it down to a decent finish. And the same, of course, applies to the flat specimens. On those, you've got to be very careful with the edges, break them, take off any swarf, and so on. So we've got our specimens, we've got a pile of the things, and we want to test them. This is a schematic of the servo-hydraulic machine. We have 10 of them in the lab, with ranges in capacity from 10 kilonewtons right up to 250 kilonewtons. If I now show you the relevant bits that do the mechanical side of it, there is the schematic of the test machine. No scale involved in this at all. It emphasizes the specimen and de-emphasizes the hydraulic actuator. But there is the specimen with an extensometer attached to it, giving us the strain signal. There is the load cell, which gives us the load signal, of course. And finally, there is the actuator, which, of course, in reality is very, very much bigger than the specimen. In reality, this is one of our test machines in our lab. can see from this, and I'll highlight the areas now. There is the specimen with extensometer attached. Close look at that will show you that above it is the load cell, below it the large thing is an alignment fixture, our speciality. That is the control panel. In the modern medium, we have a GUI, and that GUI has the knobs and buttons that would have existed on an old analog machine. We can press those buttons and sort out the loads and so on. And that is the diagnostic display. It confirms the settings that you've got. It shows you what hysteresis loops, stress versus strain plots are coming out of the machine, and tells you very rapidly if anything's going wrong. And that, as I say, is a typical test in our lab. So how do we approach this? In the middle of the 19th century, when August Werner first implicated, or can't think of the correct word to use at the moment, but identified fatigue as a means of failure in railway axles, he set forth by thinking, well, I can mimic this in the lab. I'll get a bar of the material, I'll rotate it, and I'll hang a load off the end. And that's exactly and precisely what he did. Those are rotating bending specimens. And basically he had a series of different loads and would calculate a stress on the basis of those. You can do the same in actual terms, and the result of that produces the little plot you see bottom left there. You can see from the X's on there that there are a whole series of tests at identical stresses, and that gives you the lie on the way fatigue behaves. You don't get a single life with a single stress, you get a range of lives. There's plenty of scatter, and the longer the life, the more the scatter is. That's one way of testing it. The way we do it is to do it in strain control, and there's good reasons for doing that. The control is better. And more to the point, what you're controlling is the parameter that governs fatigue, the way in which the material behaves. And what we do is we set a strain amplitude on that specimen, as determined by that extensometer, and we fatigue away. We would start roughly in the sort of middle range of lives and strain amplitudes, and work our way up and down to populate that curve. The first thing you should note from that curve is that we have not picked a series of levels. We've literally tried populating a curve to get as many at low life and as many at high life as we can to get a good fit. I've plotted here, you can see a red curve on there is the regression curve. The standard fatigue curve that you see if you're looking at the literature or anybody talking about fatigue is a regression curve. It's a line of best fit of the results that you've got. And that basically tells you that anything above that line is more than 50% likely to fail. You are 50% more than 50% or 50% confident in that. On the line, half of your components will have failed. Below that, less than half. You can't design to that. That is not actually very useful. So you have to set a level which gives you an acceptable level of failure in your component. And for this reason, we provide a design curve in the database, which there is a 97% certainty of survival with a 95% confidence interval, and that is the blue line you can see underneath it. We can, of course, in the analysis of this, choose any set of certainties of survival and confidence interval you require. For example, you can do the B10 or B5 or whatever things at a 50% confidence interval. But what we have selected gives you 6 sigma performance if you combine it with all the other effects in the design. Moving on to that, I have selected one of the examples from our premium materials database to provide you with plots. This, as you will see, sheds light. We've got 25 tests in there. You can't actually see the tests on that curve. Trust me, they're in there. The red line is the design, the 50% line, and the blue line is the design curve. And they are a decent interval apart, showing that we've got good statistical fit, good data, and so on. So how did we get to this point? I used the same collection of data to produce the calculated curves for 10 tests and 15 tests. The sort of lighter colored curve at the bottom is our design line, and the green one is the good regression line for all the data. You will notice immediately from this that if you've got a smaller number of tests, you're more likely to be, as this particular example shows, non-conservative at the short end and conservative at the long end. But equally, because of the way the dice fall when you're actually doing the testing, it could be the other way around. But the point is, the more specimens you test, the more you tend to fall onto that green curve. I mean, if we've done 30 or 40 tests, and I could demonstrate this from another set of data we have, you would see that they tend to zone down to that. And as I'll show you later, the more tests you make, the more consistent is that design line. It comes closer towards the regression line, which gives you a nice warm, fuzzy feeling. If we test those few specimens, I can demonstrate this actually via the analysis program, which shows the individual points. And what I ask you to look for on this is the way in which the regression line, which is the red line, moves up and down, and the way in which the design curve, which I have to say is not the one you saw on the preceding slide, but is calculated for this particular number of specimens. You'll notice how that moves closer to the curve as the numbers build up. That is our 25 tests. If you do 15 tests, you can see it move away. I'll go back up there just to demonstrate the thing. And you can see that if you looked at the parameters as I'm doing that, you'll see the numbers change as well, significantly in the case of the sigma F prime. So that is the reasoning behind why we do 25 specimens rather than 15, which is what we do as a compromise if we're doing it specifically for an individual group. It's a compromise between price and performance. I use this set of tests as well just to say, well, if your distribution of results is not ideal, what we do in selecting the range of values of strain amplitudes up and down, is try and ensure that we have sufficient specimens at the short life and sufficient specimens at the long life ends to really populate that curve. If you've got fewer specimens, of course, you can't do that. If I then force the issue and say, look, we've got inadequate performance here in terms of the way we've laid out those tests, you can see, looking at the green curve on there, which is the full number of tests, see what's happened to the blue and the red curves. In fact, the red curve crosses the design line. But on the whole, the design line is beneath, I will say at that point, having said that, but it crosses the curve well above 1 e to the 8 cycles with the reversals, which is a very, very long life anyway. But I can demonstrate this again by the simple reason of using the GlyphWorks analysis routine. And this is the 10 tests. Now these ones, you'll see the curves moving about and the numbers moving about. In practice, on this occasion, the design line moves in an inconsistent way because it's the way in which I selected individual examples out. Just run through that again to show you. The key thing here is to note that the red one moves up and down. Right, to summarize, we test in strain control all these data in our premium materials database. It's done to provide the required information for design life, of course, but it also provides a stress lifeline for R equals -1 as a bonus. I draw to your attention again the fact that most stress life data are presented in the literature or on the web as R equals 0.1 data. And as you vary the stress ratio up and down, of course, the line varies all over the place. So you've got to be very careful when you compare. Other word of warning at this point, stress life people talk in terms of cycles, strain life people talk in terms of reversals. And the reason for that is because of the theory, there's no difference, you just divide the number of reversals by 2 and you've got cycle. We deliver in this premium materials base both the regression parameters and that design line for all the materials that are in there. We test sufficient specimens to provide these in practice for all the materials that we've tested specifically for the PMD. There are 25 or more in there, and we will do that as we go on into the future. Right, at this point I will hand over to my colleague Paul Roberts, who will give you the lowdown on the database itself in the software.
Hello everybody, thank you Robin. I just want to carry on the presentation and look at the changes we've made within ENCODE 10 facilitated databases and also the changes to the databases we supply. Let's start off with Materials Manager. We've changed a few things in the Materials Manager which we use to access the materials databases. We've added some extra specification fields to the main generic material. So this is to allow you to have alternative specifications for each material, so I'll show you a little bit of detail in a minute. Also added a new filter option to allow you to search the materials database in terms of any of the parameters and also any of those new specifications. And also added license protection capability to the database so we can provide license protected databases. So look at the new specification fields. We've added 11 new fields to each material. So this covers things like the ISO spec, German WNR spec, so all the way through the different main specifications, and also another section in case there is a specific one that's not covered, and trade name as well. So that some of the materials where they're actually a trademark material with no other equivalent, we've put the trade name in there. So these 11 fields have been added to each material in both the current standard database and also the new premium database, and we've tried to populate as many of these as possible to give you the possibility of searching for materials a bit more easily, finding equivalent when possible. Second thing we've done is add filtering capability, so you can now search the materials database. So from the view menu there is a filter option, and this allows a simple text search on the material name or any of the specifications, selection of material type, UTS max and min, and then once a dataset type is selected, you can then select any or all of the individual numeric properties within that dataset to search on. I'll cover this in a little bit later in the demonstration, so I'll see that in a bit more detail. In terms of the standard database we supply, up until now that's had approximately 180 materials in it, 186 I think materials in it. We've now added a significant number at this release, and now there are just over 400 materials. And the materials are added are 43 datasets from the American Iron and Steel Institute and 183 FKM materials in terms of SN and DAN properties. The AISI Bar Data is a published data set of actual material tests on samples. So we took the original base data and we analysed that in our own software to come up with the curve bits and the material parameters. And we've included in that an EN line at 50% and with the scatter information and the design curve that Robin was speaking about in terms of the EN data. And also a stress life data line as well for all of those data. And all of those will have equivalent specifications in for the material set. We've also at this release added quite a lot of the FKM data from the FKM Guidelines data book. These are synthetic design curves at 97.5% certainty of survival, and now SN data and DAN materials data. So quite a lot of data sets, but actually synthetic curves, they're not actually measured data. So those both in the standard database. And we've also at this point launched a premium materials database. So this is a pretty unprecedented collection of fatigue properties for a large number of materials. Currently includes many commonly used steels and aluminiums mainly. All of these data sets were measured in our own laboratory. They're characterized in that laboratory and all using our own software to analyze the parameters. And all the fatigue parameters based on statistical estimates and scatter to enable reliability and certainty of survival to be assessed. And the plan is with this database to add materials every year, maybe probably intermediate releases during the year, and adding a total of about 20 to 30 materials per year to the database. Currently on the first release, we have 72 materials in the database, That's a mixture of 54 steels, 14 aluminiums, and 3 cast irons. And this database is currently licensed under the CDS licensing system only. And the data types included, we have the basic EN curve at 50% certainty survival and 50% confidence limit, the EN design curve at 97.5% and 95% confidence limit, and the SN data at 50% again. And all of this data will have a complete, as you see on the right, a complete set of equivalent specifications in information on the number of specimens. And that's the list of the current set of materials. As you can see, mostly steels, then some aluminiums, and then a few cast irons. This is what's currently in there. What the next set of materials to go in, you see there, this is the next one to be analysed. So a number of these have been tested already, and we're just analysing that data, and they will go in an intermediate release this year. And then we're currently adding to that list in terms of materials that we want to test, that we know should go in the database, and also significant numbers of materials that our customers have requested that are generally applicable to a number of customers. So we will try and put those data in as well. Currently, this is all room temperature data. So we've done the data at room temperature. We are currently looking at what we should do in terms of high temperature data and doing some testing on a couple of materials to begin with at high temperature. So that will be for future releases. Now do a quick software demonstration to see how that's been implemented. So here you see the premium database. So this is the list of materials in the premium database. And we now have the filter option. So the filter option is available from the View menu. So this is an example of a filter where I'm looking for a particular specification text with a UTS between a couple of values. So I have to say yes to that. There we have the range of materials found. And also you can pick individual properties from the EN dataset. So in case I want to look at the yield stretch, for example, between a couple of values, I can yield stress between 400 say and 300. So I can select on any of the numeric parameters I can select on that point. In terms of the standard database, an example of all the materials we have there, so you can see quite a long list now, about 400 materials. If I look at the FKM materials, that's the list of all the data sets we have for FKM. And the AISI database. This is the different data curves we have for that, including design curve, SN, and EN data as well.